going to start at the beginning with Albert Einstein. So he produced his general theory of relativity and published it in 1915. And this was quite a revolutionary concept that he came up with. And this reason was he completely changed the way that we thought about gravity from Newton's idea. Where Newton thought that gravity acted instantly everywhere, Einstein said this can't be possible because he proposes that the universe has a speed limit, which is the speed of light. And he also thought that gravity wasn't necessarily a force, but rather the geometry of space and time itself. And I've got a picture here that shows that how space-time can actually be deformed, and it's objects that have mass that deform space. So the more mass an object has, the greater the deformation that it creates. And as part of this theory, he also realised that actually time runs slower in a gravitational field, so your feet are aging quicker than your head, and that light is actually deflected in the presence of a gravitational field. And this is an image of the gravitational lensing effect. So despite Weber's efforts and his unsuccessful detections, this actually did inspire scientists to go on and look to detect gravitational waves and observe them directly. So here we've got two pictures of the LIGO observatories in America. The top one is Livingston and the bottom one is Hanover. And on this tiny bit of map of America, you can see that they've got slightly different orientations, and they're at opposite ends of the country. And they actually have a 10 millisecond time for light to travel from one detector to the other. So this is really good that they're so far apart, because if there's an earthquake that happened to look like a gravitational wave signal, it would be different for each detector. And the way that these work is that if a gravitational wave is to pass through, the arms would be stretched and squashed, but differently, and then you can measure the difference between them, and then that would tell us the gravitational wave signal would have arrived. And we've got a plot showing where there are other laser interferometers in the globe and ones that will be coming up. So the arms on the laser interferometer are 4 kilometers long. So what they do is a laser beam is shot down to these mirrors and it reflects back. And as a gravitational wave passes through, the lengths of the arms grow and shrink. And the laser light is in phase when it leaves because it's from the same beam. But if the distances have changed, they would actually become out of phase when they hit the detector. And this is the way that we measure that the length of the arms has been distorted somehow. And then finally, in September of last year, gravitational waves were detected for the very first time. And this was pretty much the pot at the end of the rainbow kind of discovery. It was very, very lucky. LIGO had been running for about 20 years, maybe a bit under 20 years. They had never seen anything. People were starting to wonder, will we ever see anything? Is general relativity right? And just before I started my PhD, people were saying, yeah, well, they might not be gravitational waves. Are you sure if we see them? And luckily, a month later, we actually saw them, so that was really good timing on my part. The beauty of this signal is you can really see it by eye. So the detector just went on an engineering run. It wasn't even up and running, and within a couple of days, they got this signal. So we've got this is straight from the detection paper as well. We've got the signal, the Hanford one, which was the more northerly west one on the United States, and then the Livingston one, which is in blue here. And they've been time shifted to accommodate for that 10 milliseconds. And even just overlapping by eye, you can see that they're really in coincidence. The noise has been removed, and then you start getting this really beautiful waveform arising. And then this has also been put into the frequency domain, and we have what's called a chirp, and this shows how the frequency increases of the two black holes that were detected as they got closer and closer together and finally merged. And then there's a little bit at the end on these waveforms is the ring down, because once it's one giant black hole from the two smashing together, then it's still wobbly and then it needs to stabilise, and that continues to emit gravitational waves until it's out of the realms of our detection from there. So yeah, that was really exciting. They detected two black holes. There's since been another detection, which was on Christmas Day or Boxing Day, depending on where you are in the world. And there was a trigger that was in October, or yeah, I think it was late October or November, so after this first one, which was in September. That hasn't been classified as a full gravitational wave detection because it's not significant enough in the data, but it's still triggered and it looks very much like it was another black hole, two black holes merging. So the LIGO was switched on for its first, for a second data run last week, so we should be expecting to get some new results soon, which is quite exciting. I think we'll see more black holes coalescing because they seem quite incident, and we might see two neutron stars or a mix of a neutron star and a black hole. But there are other things that LIGO might be able to detect, and one of them is spinning neutron stars. And this is where my area of research is. So first of all, I'd like to talk a bit more in depth about what a neutron star actually is. Neutron stars are formed when a star, just like our sun, explodes and dies as a supernova, and this is what's left over. They're 1.4 to 2 times the mass of the sun, and you could fit that into the size of Southampton, and that would create a neutron star. So they're incredibly dense, they have a very strong magnetic field, and they have a really strong gravitational field as well. And this makes them really interesting objects to study as physicists, because these extreme environments enable us to test the law of physics in a way that we cannot possibly replicate on Earth. So we're really putting our theories to the test of how we understand the universe. So the excuse me, the motivation behind me researching gravitational waves from spinning neutron stars comes from an observation. And it's been observed that a type of neutron star, so they're low mass, which is more than 1.4, 1.5 times the mass of the sun, that's in an accreting system, and I'll talk a bit more about accretion in a moment, that they are all spinning within a narrow frequency range of 500 to 1,000 hertz, and this is really surprising. So what I would like to do is show you a video on accretion and what this is. And this is where a neutron star will have a companion star just like our sun, and because it's got such a strong gravitational field, it'll actually draw material from the sun onto its surface. Some of that will be burnt and emitted as electromagnetic radiation. So I'm looking at ones that emit X-rays. That's accretion. You can see the material goes, and some of it will also, not all of it's burned, some of it will land on the neutron star surface. So the reason why it was such an interesting result that the neutron stars were all spinning within this narrow range is because there will be a transfer of angular momentum. So we'd expect the neutron stars to be spinning much faster, and they'd have a more broad range of frequencies, spin frequencies, depending for how long they've actually been accreting. And we'd expect them to be spinning so fast they'd be close to breaking up. But something's stopping them from getting faster. And we think that's because gravitational wave emissions become important, and they're losing energy as gravitational waves, so that's causing them to slow down. So the spin up is balanced by the spin down of the gravitational waves. neutron stars, to produce gravitational waves, they need to deform from their symmetry. And one way this can occur is through mountain growth. So a mountain that grows on a neutron star can produce a gravitational wave signal that's detectable at Earth if that mountain is a few millimeters in height, which I think is quite incredible. And that just goes to show how dense these neutron stars are. But for the mountains to grow, we need the neutron star to change in some way. And for that to happen, we need, one of the ideas is that we need hotspots to arise in a neutron star. And this can happen through accretion and also through the neutron star's magnetic field. So the reason why we need hotspots is that there's a process that neutron stars undergo called electron capture. And this is where a proton will capture an electron and turn into a neutron and produce a neutrino. And this is how they increase in density. And so this electron capture reaction is very density sensitive, but it's not very temperature sensitive. Only when it's at extremely high temperatures, about 10 to the 8 Kelvin. Unfortunately for me, a neutron star crust is at 5 times 10 to the 8 Kelvin. So any slight temperature increase on that might be enough to affect these reactions and where they occur. So I've got a diagram where I can show a bit more as to how these mountains would actually grow. If you use the dashed line as a line of separation, we've got a lower density and a higher density here because the density increases as you go towards the center of the neutron star. So the electron capture would happen in this region. But if it's got slight hotspots, then it can actually start forming in this region above the dashed line. And this creates a density variation. And then as the density varies, the crust will actually adjust elastically to accommodate for that. And this is what gives rise to these deformations and the distribution of mass changing. So I've mentioned that accretion might be one of the ways that these hotspots can arise. And the way that this occurs is that if you have a box of accreted matter and that falls onto the neutron star, more matter will be accreted and land on top of it. So the box of matter will undergo compression, and then nuclear reactions will start to occur, and it will start changing density, and it will go through the neutron star crust. Well, those nuclear reactions that are occurring actually generate heat, and accretion doesn't tend to be even, it tends to be lumpy. So you'll get areas where there's more accretion and less, and it's the areas with more that will produce these hotspots as there's more nuclear reactions occurring. So that's one way that we can get these temperature asymmetries. Another way is through the magnetic field. So in the neutron star crust, they have these incredibly strong electric currents going through, and these electric currents generate these magnetic fields. But neutron star crusts have an uneven composition, and so there'll be varying areas of different resistivities and conductivities. And if you've got a slight area of resistivity, then as this current passes through, it will lose energy in the form of heat. But that heat, in turn, increases the resistivity. So if the heat doesn't dissipate quickly enough, then it's going to lead to a temperature runaway effect because it will keep getting hotter and add to more resistance. So that's another way that these temperature asymmetries can occur. So my actual research is looking at how these temperature asymmetries arise. I'm looking at how accretion leads to it, how the magnetic field leads to it, and also a combination of the two processes. I'm interested in seeing how long these temperature asymmetries can live for, and how big a mountain or quadrupole moment can grow in that time. And one of the issues with this is that accretion doesn't constantly happen, it switches on and off. So it's great if I've got a neutron star that accretes for 10 years and we can see it glowing and all of this, because then that gives me good chance to see how big a mountain can grow. But if it's constantly going on and off, we need to know how quickly that mountain then dissipates out. But it's also important to know how big a mountain the crust can support before it cracks, because once it cracks, then that asymmetry is broken, and then it can regain its spherical shape, so then you're back to square one. So why study gravitational waves? It's new, it's exciting, it proves Einstein's theory. I really like it, sounds cool, but there's a bit more to it than that. The title of my talk is It's a New Window to Our Universe, but I haven't explained why. Like, what does gravitational waves offer that electromagnetic radiation doesn't? And this is something that I think is really nice, and it's not taught at schools, which I don't know, but still. So at school, we're taught that gravity acts between masses. It's pretty fine, even Newton came up with that one. But Einstein said energy and mass are the same thing. So if we rearrange E equals mc squared and put it in, we get this equation, which says actually gravity acts between energy. And for anything to exist, it must have energy. So everything in our universe has energy, so gravitational waves can interact with everything, which means we can illuminate dark matter and black holes, and who knows what else we're going to find. And that's what I think is really exciting about gravitational wave astronomy. So what does the future hold? Well, just like electromagnetic radiation, we have a spectrum, and we have a gravitational wave spectrum. And this depends on the frequency of the signal. So the spinning neutron stars come into our terrestrial observatories, which is pretty handy, but unfortunately I don't think we'll be detecting them anytime soon. And that's because we really don't know anything about neutron stars. We don't know their exact radius, we don't know their exact mass, and these are all constraints that we need to know to predict what the gravitational wave signal would actually look like. And I also need it to be accreting for about 10 years, because the kind of signal that spinning neutron star produces is a continuous signal. So whereas the coalescing black holes, it changes in frequency, so you get this. So whereas the coalescing black holes, it changes in frequency, so you get this. The neutron star spins at continual frequency, so you just get one of these lovely sinusoidal waves, and that's really hard to pick out of the data and out of the noise, and that's why we need it to be occurring for such a long time, so that we can extract large pieces of data and analyse it. So that's going to be quite far in the future. But the next thing that I'm really excited about is space interferometers. You may have heard that there was some technological tests to see if we are ready to put an observatory into space, and it went really, really well, and they might even bring the project forward by about 5 years. So this is looking at about 10-15 years time we'll be getting ELE set up and running. Another way that we can detect gravitational waves is by using pulsars, and we can also use the cosmic microwave background radiation to tell us more about gravitational waves and the very early universe and whether inflation occurred. So finally, I'd just like to talk to you about what life is like as a PhD student. It's going to be completely biased because I really like doing my PhD. It's really great fun. I'm in my 2nd year. It's quite different to undergraduate in that the stress levels, I'd say, are quite different. As an undergraduate, you have peaks and troughs. You have peaks when you've got your exams and you're cramming over Christmas, and then it's super chill all summer for like 3 months, which is amazing. So the downside is I don't get holidays in that same way for such a long time, but the plus side is I don't have exams. So the kind of stress you're under is more of a continued one, which I think is healthy for me. I don't know about you guys. On a daily basis, I try and vary my day. So sometimes I do reading, sometimes I do a bit of teaching, which I really enjoy, and I get paid for it. Other times I have to do marking, which I just get paid for. I check the archive. For those of you that don't know about it, that's like the front page for research news, see what people have been releasing, where their papers, what papers have been released. I do quite a bit of coding now that I've learned. And I do a lot of equations. I'll check what the maths is in different research papers so I can mix it up. I see my supervisor about 1.7 times a week and he's really supportive. So yeah, in those ways I really enjoy it, it's great. But I think one of the things, if you're considering doing a PhD, is why you actually want to do a PhD. You might want to stay at uni for as long as possible. You might want to be called a doctor, which are great reasons, but they're not the most valuable reasons as to why you should do a PhD. You've really got to love what you do. You're going to spend 3 to 4 years studying one thing. And the more you learn, the narrower you go. And that can be tricky if you're not enjoying what you're doing. And the other thing about being a PhD student is you're entirely self-motivated. No one's going to tell you you're not doing anything. You've got your funding, but you could still take longer than that. It's up to you how you go about it. So if you're not enjoying it and you don't have anybody telling you to get out of bed and come into work, that can be really difficult. But fortunately, I knew what I wanted to do. I worked really hard to achieve that, and I was really lucky to actually get the position that I really wanted. So you really need to eat, breathe, sleep, and love what you're doing. That doesn't mean you don't have time for anything else, but you just got to make sure you love that. And then you've got to look at reasons as to why you might not want to do a PhD. Money is not where it's at here. And with that, it's also job stability. If you want to be an academic and go through that whole career path, it's fine when you do your PhD, but after that you need to do postdocs, and these are placements for 1 to 2 years, and you just keep doing that until you get a permanent position, and you need to be ready to travel around the world to get those